Okay, let's see. Let's get going. So today we're gonna be talking about ionic compounds. And so, as just like yesterday, I'm gonna start with yet another periodic table drawing. And we're gonna start by going over um, the ions that certain elements will tend to form. So we remember that everything in group one, the alkali metals, they had one valence electron, right? And they were one, um, for example, potassium was like argon 4s1, sodium would be neon 3s1, and so forth. Yeah, I know. I'm going to be a master of periodic table drawing by the end of all this stuff. We're going to see that those being metals will tend to lose their one valence electron in order to become like noble gases. And so we're going to see that everything in the alkali metals, with perhaps the exception of hydrogen, is always going to form a +1 ion in a chemical reaction. And similarly, we're going to see that everything in the second column is going to form a +2 ion. They're going to lose 2 electrons to become like a noble gas. So that would be something that like calcium, which is argon 4s2, it's going to lose those 2 s electrons and become a +2 ion. Similarly, if we go, here, let me draw some lovely columns here. Okay, so that's noble gases there. There's our halogens, chalcogens, 15, 14, 13. Okay, cool. So remember we had the group numbers. Our noble gases are not going to form ions, of course, because they are already noble gases. They have no need to gain or lose electrons. It just would not make any sense. They're already kind of happy, as it were. What color have I been in? This is blue, I think? Yeah. We're going to see that on the other side of things, our halogens are going to form -1 ions because they only need one more electron to become like noble gases. And similarly, we're going to see groups 15 and 16 will also kind of form predictable ions. And so we're going to see that these ones are always going to be kind of exact. So everything that we see that's within these columns are going to form ions of fixed charges. Group 1, 2, 15, 6, and 17 form fixed charge ions. So that means in every situation, when these guys are forming ions, they will only form these specific ions. We're going to see we have a few more that will always form specific ions as well. We're going to see that aluminum here zinc and silver will happily form a little pattern for us. Aluminum is going to be 3 plus. Zinc is always going to be 2 plus. And silver will always be 1 plus in an ionic compound, as we're going to see. We're going to learn how to form ionic compounds in a little bit. Just so you know, also cadmium, which is right below zinc, will also be +2. And so we're going to see that anything not listed above can have variable charge ions. And so we're going to see that, for example, iron, which is going to be somewhere in the middle of our transition metals there, it tends to form two different ions. It could form a +2 ion or a +3 ion. Some like copper, for example, will form a +1 or a +2 ion. Some form even crazier ones. Manganese will form a +2, a +4, or a +7 one, most commonly. And you'll also see chromium was often going to 3 or 6. There's all sorts of different ones that these ones could form. And so there's not a hard and fast rule for predicting what charge those are going to be. If you go ahead and look in Canvas, Canvas will have it too, but that summary of ion things that I told you guys about yesterday that's been in Discord, if you look on the first page, you're going to see a bunch of different charges on that. Yes, correct. There will be specific examples where fluorine in particular will be able to mess with noble gases, but by and large, noble gases do not react. You have to do some pretty crazy things to get them to do stuff. So we're not going to necessarily worry about that. So if we go ahead and look on, let me see if I have this ready to share with you guys. I think it's window capture 3. Let's find out. Yeah, it is. Okay. So we're going to see here in a much better drawn way that's summary of ions things that I gave to you guys. This will have kind of the fixed charge elements for you. You're going to see that some of them, like iron and cobalt and all that in there, in that orange, light orange section, that have some of the multiple charges. Just so you know, those ones could do more than those ones. So chromium, for example, it says here +2, +3. Those are just very common ones. We're going to see chromium definitely could do others. We're going to see chromium can do +6. That's pretty common. Manganese can do +7. Like I said, you're going to have all sorts of different ones. So essentially what you guys need to know are the fixed charge ones. So the ones that only have one charge, that means they only have one charge. So those ones will always be the same. It's the ones that have variable charges that could be different, and so we'll see that those will be calculated, as we're going to see. You'll see on the right side of this, there is what we see systematic names and Latin names. I'm not going to make you memorize these Latin names. They're kind of old, only old. I mean, I understand we have some older students here, but like that stuff is from way back when in like the 40s and stuff. So somehow some of the names have still come around, like ferric is still kind of used here and there. And actually, if you go ahead and look on your toothpaste, sometimes you'll see stannous fluoride is the active ingredient. Some of them use sodium fluoride, some use stannous fluoride. So they'll see those names are kind of still hanging around, but they're not preferred. And you'll also see there are some common compounds up on the top there. These are often ones that you'll see in real life or chemistry. And so those would be a good idea to be familiar with. Okay, and last thing on this particular chart, we're going to see 7 elements do always exist as pairs. You know that oxygen is O2. It does not form oxygen by itself. That's just something to keep in mind. We'll talk about that more when we get to chemical reactions later on. Okay, so that's everything on this page. On the second page, again, there's that polyatomic ion chart. Like I mentioned last time, it will be very much to your interest to learn this. You will see that there are patterns for some of these, like example, this kind of bottom section down here. you can see patterns going from the names of certain ions. And some of them, it's just kind of, you'll have to learn them. So I'll leave that up to you to work with, but we will definitely be referencing this all over the time, all over the this chapter and in the future. And then we're also going to see that on the left side of this chart are going to be a bunch of rules for how to name compounds. And we're going to go through these rules today and tomorrow. And we're going to see that all of these rules are written out here, so it's super easy access for you guys to take a look at. But we're going to have tons of practice with this. You'll forgive me, but you're going to have hundreds of homework problems on this because this is a particularly important skill for you to come away with. It makes it a lot easier if I can just say the name of a compound and you understand what the formula is, rather than trying to say the formula each time. Okay, so that being said, let's start learning. Okay, so that worksheet or that handout thing is there for you guys, easy access for you. All right, so let's see how we form ionic compounds. One thing to note is that, let's see, I'm going to do this in dark blue. All compounds are neutral. That means overall, the charges cancel out. Okay, so all compounds are going to be neutral because their charges will cancel out. Okay, that is true for, compounds by definition must be neutral, but they will not have charges if they're not ionic. We're going to see examples of that probably tomorrow. But today we're talking about ionic compounds. So, ionic compounds generally follow this form. They're going to be a metal ion plus a non-metal ion. Remember that typically your metal ion is the cation and your non-metal will be the anion. We always say the positive one first. Okay, so that's convention. We always say the positive one first. And one thing to note that we'll get into later, either ion or both could be replaced by a polyatomic ion. So just so you know, those polyatomic ions in that big old chart could take the place of either the metal ion, if it's a positive polyatomic ion, or they could replace the non-metal ion, and that would be the case of something that's negatively charged. Okay, so let's go ahead and see how these things are going to come together. If we have a sodium ion and a chloride ion, let's see how these two will come together. This one will be super nice and easy for us. We see that the charges of sodium and chlorine here are going to be, they're equal but opposite, right? They're both, what, sodium's +1, chloride's -1. If we think how many of each we need to kind of balance things out, we only need one of each, right? We know that this will come together to form this compound. We have one sodium, one chlorine in there. They are equally in the same ratio. All right. However, if we took a different element that had a different charge, we're going to see that we have to do a little bit of math here. It's not real math. It's very basic math. So we have to think to each other, how are we going to make it so that sodium can balance out oxygen? And how we're going to do that is technically by finding the least common multiple. And if we don't remember our math from whenever we learn least common multiple, that's just that just means that we're going to try to find the smallest ratio that's going to make these balance out. And what that means is that we're looking at the numbers 1 and 2, and we're going to see what's the smallest number that's divisible by both 1 and 2. And of course that's going to be 2, right? 2 is divisible by 2, and everything is divisible by 1. So that tells us that we need our charges to be plus 2 and minus 2. That's our least common multiple here. And so we're going to be able to get sodium to be plus 2 by having 2 of them. One oxygen by itself already has the minus 2, but we're going to need 2 sodium ions to balance that out. And so we end up writing this as Na2O. This process is called charge balancing, by the way. Again, I mean, this one may have been super obvious to you. You see one of them is twice as big as the other. You're going to need 2 times as many to balance it out. Things can get maybe a little bit more complicated when we have bigger charges, but the process is the same here. If we look at the least common multiple, as in what's the smallest number divisible by 2 and 3, that's going to be 6, right? So our least common multiple is 6. So we're going to need 6 plus and 6 minus here. So that's going to tell us we need 3 calciums and 2 nitrogens to balance that out. Putting that together, we get this arrangement. 3 calciums for 2 nitrogens. And that's how these are going to balance each other out. All right, so far so good, hopefully. And so here's another example. We see this one, we have both of these are already 2. They are already their least common multiple. And so we just need to put them together. One thing to note is that all ionic compounds are empirical formulas. And that means the lowest ratio possible is used. So that means we will never see something like this. We're never going to see, there's really no point to doing that. And we're not going to see that one either. Or, you know, we're never going to see that either. We always want to use the lowest possible ratio. So something like this one would also not be good, because this is not an empirical formula, right? We see these are both divisible by 2. And so if we were to draw this one correctly, it should be TiO2. That would be the correct way for displaying this particular thing. Because compounds are going to be, if they're ionic, you never really have one set. You can't have one sodium and one chlorine, right? You really have, tons of sodium atoms and an equal amount of chlorine atoms to balance it out. And so we see that we always just display the smallest ratio possible. And so that, with that in mind, I do have a little shortcut for you. If we look at, for example, this set, one way to very easily do our charge balancing is to just kind of swap. You'll take the charge of the opposite one and make it into the subscript. And so by that I mean we end up with this, where this 3 was the same as phosphorus charge, and this 2 was the same as barium's charge. So you could always do this, just crisscross it. That'll work, and that will give you a charge balanced compound. But just remember, oops. We always have the lowest ratio. So if we took that one from before, if we had or let's just take a new one, I guess. Aluminum and nitrogen. Technically, yes, we can do this. We could bring them down. But we need to remember that we still have to have the smallest ratio, so we should reduce it to ALN instead. How are we doing so far? Any questions on this charge balancing business? Okay, so I'm not seeing any. So let's see what happens when we introduce polyatomic ions into this mess, as it were. Let's take, for example, this particular set of ions. Carbonate is the one on the right there. That's part of our polyatomic ion chart. We see that that ion has a charge of -2. Our sodium has a charge of +1. We can do the crisscross, and we'll see that we end up with Na2CO3, right? We need 2 sodiums to balance out the carbonate. Hopefully nothing too crazy there. Let's look at another pair. I'll be consistent, I did that. We see here that if we were to just crisscross, we might be tempted to do something like this. However, this is not a good way to describe this, because we understand that to balance this particular calcium out, we need 2 hydroxides. right? And if we go ahead and look at this formula that we wrote here, that's telling us 1 calcium, 1 oxygen, 2 hydrogens, right? But we see here that we need actually to have 2 oxygens, right? There's 2 hydroxides there. So what this is going to actually be is we're going to use parentheses to indicate we have 2 hydroxides. If you have more than one copy of a polyatomic ion. So with the carbonate, we only had 1 carbonate in there, so we do not need to put parentheses. And in fact, it would be, dare I say, wrong to put parentheses there. The chemists, myself included, love brevity, right? We like to make stuff as short as possible, as simple as possible. So we do not put parentheses if we don't need them. Okay, but if we have multiple of a polyatomic ion, we are going to use parentheses to indicate that we have multiples there. So let's take a look at this one now. So we can crisscross. If we do that, oops, I've misdone that. Again, we don't want to put 42 oxygens. That would be quite absurd, right? So we're going to have to put in our parentheses to understand that there are 2 of that phosphate ion for 3 magnesiums. Okay, and so just to make sure that we completely understand this chemical formula stuff, this thing has 3 magnesiums, it has 2 phosphorus, and 8 oxygen. So that 2 outside the parentheses, if we were to look at how many atoms of each type there are in this particular compound, that 2 outside the parentheses gets carried over. So it does mean that there are 2 phosphates overall. Okay? Let's do something a little bit more interesting, perhaps. Okay, yeah, here's one. So we've got a tricky one for you now. If we charge balance this, this is what we get. One thing that's very, very important to note is that this 2 is part of the polyatomic ion. Whereas this 2 is from charge balancing. Because these 2's represent different things, we can't reduce this. We cannot reduce that to NaO because those 2's mean different things. That 2 on the oxygen is part of the polyatomic ion peroxide. And we're going to see that that is very different than just plain old oxide. And since the 2 from sodium comes from charge balancing, they're different. it's important that we kind of consider which subscripts are part of polyatomic ions and which ones are from charge balancing. If we were to look at this just to make sure things are super clear, like if I wanted to be super obvious, which again we would not do, we are not going to put parentheses on this guy. This is why we can't reduce it, because the subscripts are not actually the same. So the subscripts, meaning how many of each one there are not the same, so we cannot reduce it. Okay, let me just mark these parentheses are just for explaining. Explaining the parentheses. Alrighty, let's do some current events now. We could also have two polyatomic ions that come together. And the idea is the same. We would charge balance them appropriately. And so you'll look at this and you say, well, hey, you've got two nitrogens there. Let's combine them together. We don't do that. So we are not gonna we're not gonna do anything like that. Anytime we have polyatomic ions, we are going to keep them kind of nice and happy separate. So this one is made of the ammonium ion and the nitrate ion. We're going to see this is called ammonium nitrate as a result. And so we describe that by keeping our polyatomic ions as kind of separate units. All right. Just, stop me if this is going too fast or anything. But otherwise, I'm just going to keep on going. More examples, more practice. So, one more thing we can do with this is we could use chemical charges, or rather the chemical formulas, to determine the charge if we have a metal that has a variable charge. Remember, iron is not one of our fixed charge elements, so iron could have a whole bunch of different charges. And we need to be able to distinguish between them because we're going to see those have different properties. If we look here, what's going to be the charge of iron in each case? We can look at that. We know that oxygen is always -2 when it is a simple ion. And we see here that iron and oxygen, we have the same number of each one. So that tells us, therefore, that this iron must be +2. Because these guys have to cancel out. If we look at the one on the right, we know again oxygen has a fixed charge of -2. As a simple ion. And so 3 of them overall is -6, right? And because we must always, always, always make sure things are balanced properly, this tells us that this positive part must be +6. And since we have 2 of those irons, we see that means each iron is going to be plus 3. We have total of plus 6. We have 2 irons, so that means each iron is plus 3. All right, another way we could have done this in purple, why not? We could have said 2 irons plus 3 oxygens has to equal 0. Just remember the charges, again, have to always cancel out. We know that oxygen, here, I'll make the zeros more obvious, likes to be -2. And so we can use these chemical formulas to figure out what the charges are of variable charged elements. So just using some algebra, because these guys have to cancel out, we can do that. We have, of course, a shortcut. Just like before, we were able to crisscross things. We'll use green this time. We can go backwards too. And so we can see that we end up with these guys. One thing to worry about, though, however, if you're going to do this kind of reverse crisscross, we always want to double check if we're going to try and when crisscrossing. Because if we had something like this guy, so technically our subscripts are 1 and 1, right? If we were to crisscross, you might be tempted to say, okay, look, we have chromium plus, oxygen minus. One thing to note, oxygen is not going to be -1. It has to be -2 by itself. And so this is that double checking idea, is that because if we just crisscross this and stop, that tells us oxygen is -1. But since we know it must be +2, or sorry, -2, we're going to have to multiply everything by 2. So what we actually get is chromium 2+ and oxygen 2-. And now we are happy and double checked. Of course, we could have used the algebra way to do this. That will always work. But I know a lot of people like to kind of find shortcuts. And so this is one way to do that. You just have to double check. Make sure that you're not violating any of the fixed charge elements. Okay. So far, so good? This math is nice, a lot easier than any of that mole stuff. So, totally get you there. Okay. So now we're going to finally get into how to name these guys. For metals, naming is super easy for us. This dude is called sodium. This one is called a sodium ion. This thing is called calcium. This is called a calcium ion. We don't reduce it down because oxygen is diatomic. Where are you? From which one? Sharia, I'm not quite sure. You mean like this one here? The like sodium peroxide thing? If so, in this case, yes, the oxygen is part of a diatomic ion, though we just usually call these polyatomics. Oh. So the charges we don't reduce. If we were to put these together, sorry, I'll just do it down here and I'll erase it. Okay. So if we're putting these guys together and you crisscross, you should get the same compound that you started with. Oops. So you would technically get this, but understanding that we don't have the polyatomic ion here, that just becomes CRO. Is that what you were asking? Just wanted to make sure. Okay, cool. In that case, this is going bye-bye just because, yeah. Cool, okay. So, our fixed charge metals, just add the word ion to the end. That's it. I'm going to just make that a little bigger because it's kind of squished. Ion. These are both iron. This one we call an iron 2 ion. And this one we'll call an iron 3 ion. We use Roman numerals to indicate the charge of a variable charge element. We'll call this one a lead 4 ion. This one will be a... This one would be a chromium 6 ion. So whenever we have if the metal has variable charge, write the charge, oops, with Roman numerals. Does everybody remember their Roman numerals, by the way? I'll do them real quick. Oops, I don't want purple for that. I want dark blue. Yeah, let's do dark blue. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that is just there's our Roman numeral reminder. So that's what those look like, in case you've forgotten. Okay, so the last part of our naming before we actually put them together is nonmetals. Oops. We know that chlorine forms -1, sulfur forms -2, oxygen forms -2, nitrogen forms -3. These guys are chlorine, sulfur, oxygen, and nitrogen. Notice these guys, we do change the name a little bit. Whereas with the metals, if sodium became charged, we just call it sodium ion. Or barium, we would call it a barium ion. With non-metals, we will change the ending to be "ide," and that is just convention. It's a way of describing negative ions. So they have this "ide" ending. So you'll typically drop the last syllable and replace it with "ide." So like sulfur became sulfide, nitrogen became nitride. If we had hydrogen, it would become hydride. I guess since we're here, hydrogen is a little special. Oops. Oh my goodness. Go away. There. Remember that hydrogen could go plus. Hydrogen is kind of really the only one of the non-metals that could go plus. It's special. And this one we will actually call a hydrogen ion. So positive ones don't change the name. The negative ones will change their ending. Okay. Let's actually put this stuff together. Here is our favorite ionic compound, one that we all know. We are very familiar with this guy. We know that the name of this is sodium chloride. Yes, this is something we are terribly familiar with. This came from sodium ion plus chloride ion. We are just going to remove the words ion, just because this is going to be an ionic compound. And so we just call this sodium chloride. Boom, easy. We see that this is made up of these two. Oh, I guess I should have explained this one as Na plus and Cl minus. So hopefully that was obvious. We know that this guy is a sodium ion. And this guy is the bicarbonate ion from our polyatomic chart list. And so putting those together, this becomes sodium bicarbonate. You'll see that bicarbonate could also be called hydrogen carbonate. You could call this sodium hydrogen carbonate. That would work. Same thing. Let's just leave that off for now. Just so you know, this is baking soda. In case you want to amuse your friends or whatever. So with that being said, let's do a few practice ones. One thing to notice is if you ever have more than 2 ions, at least one of them must be, or rather, more than 2 elements, at least one of them is a polyatomic ion. So KCl is just potassium ion chloride ion. All of these potassium's going to be plus, right? Potassium doesn't change. We see that the rest of this stuff must be from polyatomic ions. We would have to look on our list to name these, but we're going to see that this one would be potassium chloride. Remember that just the negative charged element takes that "ide" ending. For the other two, we would technically have to go to our little chart here and be like, okay, look, here is, where are we? ClO2 minus. Am I way up there? Sorry. I have like 2 mice showing on this thing. Sorry. So we'll see ClO2 minus and ClO3 minus are right here on our polyatomic ion chart. And we see that ClO2 minus is called chlorite, and ClO3 minus is called chlorate. And so, this must be potassium chlorite, potassium chlorate. Again, for ionic compounds, we just put the two names of the ions. That's it. And so we're going to see here spelling is important, right? These are very different compounds. If you eat potassium chloride, it'll be a little bitter, but chances are you'll be fine. However, if you eat potassium chlorite, or worse, chlorate, you'll probably die a lot more quickly. Just because those oxygens on the chlorine tend to make it behave very differently. That's much more similar to bleach, for example. If you have this is sodium chloride, this is sodium hypochlorite. ClO minus is hypochlorite. This one is bleach. This one is, table salt, right? You eat your table salt, you'll be fine. You eat your bleach, you die. So it's very important that we know how to name these properly, because if you're messing with the wrong compound, bad things could happen. So that's why we're doing this. That's why we're going to spend a lot of time doing it too. So let's do a couple more. Oh, so now we cannot say chromium sulfate. Why can we not say chromium sulfate here? And why can we not just say cobalt phosphate? Again, angry face. This one has kind of a unibrow, but that's okay. Why can we not say these like this? Any ideas? No, because of the O4, not really. It has more to do with the metals. Like for sure, SO4 2 minus is sulfate, and PO4 3 minus will always be phosphate. It's not necessarily, well, kind of. We're getting there. So this thing is always sulfate. No problem. This thing is always phosphate. So anytime I give you a chemical formula, it will be balanced. Okay, so I'll just tell you guys since we are almost out of time. The reason is because these guys, cobalt and chromium, are variable charged elements. And anytime we have a variable charge element, we need to talk about the charge with the Roman numerals. So, because sulfate is SO4 2 minus, that tells us that this must be chromium 2 plus. They have to balance out, right? I have not given you any subscripts with this one, so that tells you the charges are the same. This one, remember, is chromium 2. And so, if we were to really make this a correct name, we would have to say chromium 2 sulfate. Right, this was the sulfate ion, this is the chromium 2 ion. So if we're to put those guys together, we have to make sure that we indicate the 2. And the same thing here, we will figure out that cobalt is 2 plus. We can get this from crisscross or algebra. And so, again, this one will be cobalt 2 phosphate. So whenever we have these variable charge elements, the transition metals mostly, there are a few that are not transition metals, but when we do have transition metals, we always have to indicate the charge, because we're going to see that chromium could do all sorts of crap. Let's see if I want to make this one. We'll see that all of these are different compounds. And so they have to have different names. And so since we are out of time, I'll just go ahead and write them. You know, this one would be chromium 2 sulfate. This one would be chromium 3 sulfate. And this one is going to be chromium 6 sulfate. So These all will have different names because chromium could have different charges. So anytime you've got potential different charges, you must use Roman numerals to indicate what the charge is in this case, in the case of the compound you are given. Okay, we are all out of time today. We are going to continue naming tomorrow. So we'll start off with some practice. In fact, I'm going to go ahead and put your homework up right now, or rather in like an hour or two, but it'll come up today. And you're going to see that you can do some of these already right off the bat, but we will continue doing more practice tomorrow, and we have kind of 2 more classes of compounds to name. In case you forget the rules, don't forget they are, happily for us, it's right here. For us, we've gone through ionic compounds today. We always put the metal first, followed by non-metal with "ide." And if we have something that has different charges, multiple charges, or variable charges, we must put the Roman numeral to identify that charge. Okay, so that, again, is going to be our handy list. Again, your life will be a lot easier if you either commit this table to memory or make a handy little sign and post it on your wall right next to your computer or something for easy access. Okay, with that, I did put a discussion prompt for you guys, so just tell me what's next for you guys. If you're transferring, like if that's your plan, if you plan to, whatever you want to do in the future, just drop that. We'll see. It looks like some of you have similar plans, and it's good to see you guys like discussing them. So that's cool. Okay, I will see you guys tomorrow. By the way, just so you know, this week we will probably do a Thursday lecture just to really make sure we've got the naming down. So again, if you can't make it, no worries. It'll be recorded so you can watch it later. But just I am planning that as of right now. So Thursday I will be on for you guys at 9 o'clock. Alrighty, take care, everyone.